Imagine surgery with unparalleled precision. That's the promise of robotic surgery, where physics takes the center stage. These marvels of engineering manipulate instruments with forces, torque, and incredible control using various sensors, operating within the human body through tiny incisions. This is ANUKRITI SETHI, and I am a third year undergraduate student doing my BTech in Engineering Physics from IIT Roorkee. Since my first year, I am fascinated by the fusion of physics and medicine. Today, let's explore the advantages robotic surgery brings to patients and surgeons. Buckle up for a mini voyage into the future of medicine and surgery where physics holds the scalpel.
So let's begin to delve into the world of robotic technology, the robotic surgery. Surgery, the art and science of operating on the body, boasts a rich history that stretches back millennia. Starting from the ancient times till the 18th century, the freehand surgery was the method that was used. Then, from the 19th century onwards, the minimally invasive surgery or the laparoscopic surgery developed. Then was the rise of the robots from the mid 20th century, which made the assisted surgery or the robotic surgery possible, which is still in development today. In the future of surgery is automation, all about the AI powered robots. So, what is the robotic surgery? Let us see. Robotic surgery is a cutting edge technology that is revolutionizing the field of surgery. Unlike traditional open surgery, which requires large incisions, robotic surgery uses a minimally invasive approach. The surgeon sits at a console, completely separate from the patient and manipulates the robotic arms using hand and foot controls. These robotic arms are equipped with tiny surgical instruments and a high definition camera, allowing the surgeon to see the surgical site in magnified 3D detail. Laparoscopic surgery allowed surgeons to perform complex procedures through small incisions, reducing patient pain and recovery time. However, it has some limitations. The long, slender instruments used in laparoscopic surgery can be difficult to maneuver, especially in tight spaces. This lack of dexterity can limit the types of procedures that can be performed laparoscopically. Additionally, the surgeon must maintain an awkward posture for extended periods while operating, which can lead to fatigue and discomfort. Finally, the 2D view can limit depth perception and make it difficult for the surgeon to visualize complex anatomical structures. Robotic surgery builds upon the benefits of laparoscopic surgery by addressing these limitations. This is the picture of the Da Vinci surgical system. The Da Vinci surgical system is currently considered the most successful robotic surgery system. It has been widely utilized in multiple anatomic regions. It is composed of mainly three units: the surgeon console, the patient cart, and the vision cart. Now let us see the various components of the robotic surgery. The eye tracking system. The eye tracker monitors the surgeon's eye movements, translating where they are looking into. This data then can be used for various purposes. Firstly, to control the instrument movement by looking at specific areas on the surgical field displayed on the console, the surgeon could potentially control robotic instruments, freeing up their hands for other tasks. Secondly, to enhance the information display, the system could overlay relevant information based on where the surgeon is looking, reducing the need to constantly shift focus between the surgical field and other displays. Thirdly, to improve the workflow, eye tracking could streamline tasks by allowing surgeons to activate functions or select instruments with a glance. The various components in this eye tracking system are: The sensors, typically small, near-infrared cameras, are positioned near the surgeon's face. These cameras emit invisible near-infrared light. This light reflects off the cornea and the pupil. By analyzing the pattern of reflection, the camera can determine the direction of the surgeon's gaze. In the processing unit, the captured data is processed to calculate the surgeon's point of focus on the console display. The software then translates the actionable commands for the robotic system. Moving on to the haptic feedback system. During surgery, surgeons rely heavily on touch to understand tissue texture, grasp delicate structures. Traditional surgery provides this vital feedback naturally through the hands. However, robotic arms lack this inherent ability. Haptic feedback bridges this gap. Several sensors play a role in haptic feedback. The force sensors, which are embedded in the robotic arms end effectors, detect forces applied to the instruments during tissue interaction. The joint position sensors track the position and movement of the robotic joints, providing information about the instrument's orientation and path. Actuators are a part of device which achieves physical movements in a mechanical part in the robots. In the context of surgical tools, actuators are strategically positioned remotely from the end effector and surgical sites, providing a safe and straightforward solution for lightweight instruments to operate within the confines of the human body. The cable actuators, the fluidic actuators, the smart material actuators, the magnetic actuators, and the electrical actuators are some of the actuators that are used in robotic surgeries. Sensors are the eyes and ears of the robot assisted surgeries, providing crucial information about the surgical environment and the state of the robotic system. Firstly, the joint position sensors. These sensors track the position and movement of each robotic arm joint. They typically use technologies like the encoders and potentiometers. The encoders generate electrical signals corresponding to the joint's rotational angle. The potentiometers measure the voltage drop across a resistive track as the joint rotates, providing a continuous position reading. This sensor data is essential for closed loop control and kinematic calculations. The robotic control system uses this data to ensure the arms move precisely according to the surgeon's command. The force sensors. These measure the forces applied to the robotic arms, particularly at the end effectors. Common types include strain gauges and piezoelectric sensors. Strain gauges are embedded in the instrument shaft and measure deformation caused by applied forces. Piezoelectric sensors convert pressure exerted on them into electrical signals. The vision sensors provide visual information about the surgical field. There are two main types: endoscopic cameras and 3D cameras. The endoscopic cameras are small, high resolution cameras which are integrated into the surgical instruments, providing magnified views of the surgical site. There are also certain other sensors like the tactile sensors and the temperature sensors. The tactile sensors are under development and aim to provide more nuanced information about tissue texture beyond just force. They could potentially use technologies like microfluidic sensors or biomimetic tactile sensors. The temperature sensors monitor the temperature of the robotic instruments to prevent overheating and potential tissue damage. Imagine a team of intelligent robots, not a human surgeon, meticulously performing a delicate laparoscopic procedure. That's the fully automated surgery, which has great potential to develop and scale up to great levels. These robots will be equipped with the haptic technology, swarm robotics, sensory perception, and AI and machine learning. As research and development progress, automated surgery has the potential to redefine the landscape of surgery, making it safer, more effective, and available to a wider range of patients around the world. That was all about this fascinating arena of robots. Thank you.